All right, I am very excited. I have a new toy to play with on my iPad, so that's going to be fun. I was waiting for that to get approved, and now it is, which is exciting. All right, we are going to go ahead and start. So 3.1, looking at measures of central tendency, about on average, what do we see in terms of our data. 3.2, kind of taking some of those ideas and generalizing them, mostly for the median. 3.2 kind of revolved around kind of that median metric. And what we're going to establish in 3.3 and kind of beyond is a fairly similar framework for what we got for the median. That last kind of measure of position, z-scores, are ultimately what we are building to. But before we talk about z-scores, we have to talk about kind of differences that we might see amongst the variation of a particular distribution. So let's start with, we're going to start with an example, see what we can kind of infer from this particular example. We are given two data sets, and we're going to just start with trying to figure out what the mean, what the average, the middle of these data sets is going to be. So take a moment, figure out what are the X bars for data set 1 as well as for data set 2. Figure out those numbers.
Let me think about that.
So what do we see for data set 1? What's our average? 74. And for data set 2, what do we get? So 71 would be the median, 74. But 74, adding them together, dividing by 3, would be the average. Okay, so the average is the middle, the expected value for these particular data sets are the same. Does that mean that the data sets themselves are going to be the same, or is there some kind of feature beyond just the center that would allow us to kind of compare, contrast what we see with these two data sets? What can we say that makes these two different? So we got the same result, but there's still something different between these two. What is that? Okay, so the range definitely is different. What do we notice about the range for these?
The bottom one
has a wider range, or like a larger, we might say larger spread, wider range, kind of similar idea. So maybe this bottom one we might notice is more spread out. And this top one here is maybe like more clustered. I really like that observation. So what we are going to be looking at today is a way to quantify this exact notion that we have here. That sometimes we have data that is really, really clustered around the center, where there isn't a very large range, or maybe there's a large range, but the vast majority of our data is collected around certain points, or do we see data that is instead a little bit more spread out, where maybe we have a wider range of values, so on and so forth. So measures of variation. This is going to be, what's going on here? This is going to be information about the spread of the data, which we are going to think of as important because this is going to be like supplementary information to just the center. It's like the central tendency doesn't tell the full story. It's not, may not, does not tell the full story. Instead, we need other information, in particular the variation, to get a richer sense of what is going on throughout our whole distribution. So again, central tendency does a good job of saying what's happening in the middle. This idea of variation, or as we're going to see, variance, is going to do a little bit of a good job, or at least try to start to talk about what the rest of the data looks like around that middle. Is it spread out? Is it clustered? Things of that nature. All right. The first kind of most basic notion is we're going to talk about something that Merrick mentioned here in the context of talking about spread. So kind of our preliminary idea is going to be the range of our data. So when we're talking about the range of our data, we've looked at like interquartile range, which is like the range between Q1 and Q3. What would like the overall range of our data be? What is that going to describe? Yeah, it's going to be like the distance between the minimum and the maximum. I like that a lot. So the distance, maybe like from the minimum to the maximum. Okay, so for this data set that we are given here, how would we set up figuring out our range? What, or not equation, but how would we do this? I guess kind of equation, but not really. How would we find a range here? Okay, so what's the maximum of this data set? 22. And what are we going to do with this? Which is 13.3. And what are we doing with the 2? Subtracting the 2 to figure out that our range here, the distance between max and min, is 8.7. Okay, question for you all. Why did we set it up in this way of doing like 22 minus 13.3? I'm guessing this is like what most people would default to, but why do we actually have to do this? Yeah, but why couldn't we do 13.3 minus 22? Because the flipping it is going to give us a negative number. And what am I looking for here? Looking for a distance which is always going to be positive. Okay. So note here, this must be positive because it describes a distance. Okay. We're gonna actually run into a little bit of an issue with that right now. We're gonna need to solve this issue. So range is kind of our preliminary measure of spread from start to finish. How far apart do we find the minimum and the maximum? But what we're gonna really be after here is a much more kind of fine grain way to look at the rest of the, about how that falls. And that's going to start with a look at variance. Now, ideally, variance is going to have something to do with the average distance that we see between a data point and the center of the data. So we would expect data that has a much larger spread to have a much larger average distance between data point and center. And we would expect data with a smaller spread that are like more clustered together to have a smaller average distance in that regard. The problem that we run into very quickly is that while we are looking for the distance of a data point to the center, we don't know if the data point is going to be to the right of the center or to the left of the center. And in fact, we're going to have to deal with both, right? We need to come up with a way to deal with both having data points on the left and having data points on the right. We could try and maybe say, like, if the data is greater than the center, then we do this equation, and if it's less, then we do this other one. But that starts to get a little bit complicated. I don't want to have to figure out two different equations to work with, depending on like my data. I don't want to turn this into a piecewise problem. So instead, what we need is a way to communicate that the distance is all I care about. I don't want to think about, is it positive or is it negative? I just want to focus on the distance. So what could I do that would turn both positive and negative numbers into just positive distance values? Say again? Squaring them. Okay, so ultimately, that is what we are going to do. I really, really like that. What's another way that we could do this? So we could set like a condition of like, if it's negative, then multiply by -1. That kind of runs into the problem of we like need to know when our values are on the left or when they're on the right, which isn't a huge issue. We certainly could do that. I think that that's a really good solution. What else could we do to guarantee that everything is going to be positive? Squaring is ultimately what we're going to do, but what else could we do? Well, adding it's going to make it more negative. So Merrick's idea was taking the negatives and like multiplying them by -1, which would work. We would just need to identify the negatives. So nothing wrong with that idea. It's just it comes back to that kind of piecewise definition. Absolute value would also work. For those of you who had me for pre-cal, you know absolute value and squaring are actually kind of the same thing. Not really, but are very, very much related to one another. For this particular case, mathematicians who have been dead for a very, very long time tell us that we should square these differences in order to force them to be positive rather than taking an absolute value. We could do the absolute value. There's nothing wrong with it. It would change some formulas later down the line. And I guess this maybe just gives us cleaner formulas. So we're going to go with the original idea here of squaring these differences. And so when we are talking about variance, this is going to be the average squared difference between the data and the population mean. I guess technically it doesn't need to be the population, but the formula that we're going to look at is going to use the population mean here. Actually, that's fair. I'm just going to say the mean because we'll have population mean is fine, but I'm just going to say the mean. Okay, let's take that sentence and write it in math notation. All right, let's figure out what this is actually saying in terms of math notation or what this is going to look like. So when we are talking about variance, there's a little bit of unfortunateness here where before we had like population mean and sample mean, and they were really the same thing. It's just we used mu for one of them and then we used X bar for the other. In this case, there is actually a formulaic difference and a slight, very, very subtle numerical difference between sample standard deviation and actual standard deviation, population standard deviation. They have slightly different formulas. We are going to start with the population standard deviation. So this is a population parameter. Or not standard deviation, sorry, getting ahead of myself, variance, which you will see denoted as sigma squared. It's like this little circle with like a little line on top, and we are squaring that for reasons. Now, importantly, sigma squared is literally variance, right? We're not going to square our formula. The squared is built into the variance. We're squaring something else. That's something else we're going to talk about momentarily. And just because we use the other thing rather than this, the unfortunate thing is where we start is the square. Okay. So what does it mean to take, well, first of all, we're taking the average of a bunch of squared distances. So if I'm looking at that, this is going to be like, here, we'll put it down here. This is going to be from the data minus, if I'm talking about the population mean for my population parameter, for my population variance, what should I use to represent mean? X bar would be sample. Mu is what we're going to use to represent the mean here. Am I just looking at the difference? What do I need to do with this? We have to, well, we're getting ahead of ourselves a little bit, but that is what we're working to, yes. So we're squaring it. Why do we square it? Guarantees that it's positive. That's all we need to worry about there. And then we want to take the average of every single time we do this. So what is taking the average mean? Dividing by n after we add them all together, divide by n. Perfect. So we are going to sum big sigma, all of these square differences together, and then at the end, we are going to divide by n. That's literally just taking this statement, the average squared difference between our data and the mean, and writing it as an equation. That's what the notation will look like for that. We should have a relatively short lesson, so if you want to wait to the end of the lesson, yeah, you can, or you can go out. Either way. Okay. I want to show this in action because the process itself is actually fairly straightforward. And then I also want to take a look at what this is actually trying to say, what this actually means. So let's consider our two data sets from before. So we had data set 1, where we said, what was the X bar that we saw for that? What was the mean? 74. And then we had data set 2, which also had the mean of 74. If I'm trying to calculate the variance, the average squared difference between these two, this variance squared is going to be in this case. Now, technically, if this were a sample, I should be using the other one. We'll assume it's a population for now. So let's actually replace these X bars with mu's while we're here. We'll assume, sure, that this is actually a population that has 3 people in it. Why not? All right, so the difference between the middle, the mu, and our data, for that first data point, that will be 72 minus 74 squared. For the second, it will be 74 minus 74 squared. And for the third, it will be 76 minus 74 squared. And what am I doing to this? To take the average, divide by 3. 72 minus 74 is -2. Squared is 4. 74 minus 74 squared, 0. And then 76 minus 74 squared is another 4. 8 over 3 is 2.3 repeating. Say again? Oh, you can write this in the margins of page 1 if you want to. I'm just trying to show you how this actually works. There's also a page later on that's called comparing the spread of data sets. You could write this here if you want to, because this is ultimately what I'm skipping this section in this demonstration. So you could write it there if you want to. Okay. What does that 2.3 repeating mean? We have no idea. We don't have a good interpretation yet for what this value actually represents. And ultimately, this is not the value that we are going to use. We're going to modify this ever so slightly before it's usable. But by the end of today, we still won't know what to do with this. That's context for what we are going to be doing momentarily. But let's continue with set 2, and let's just see if we can make some kind of general notes about what we see. So same process, figuring out our sigma squared. In this case, we see 59 minus 74 squared plus 71 minus 74 squared plus 92 minus 74 squared. All divided by, that's awful, that worked out. All divided by, again, 3. 59 minus 74 is 15 squared is 225. 71 minus 74 is -3 squared is +9. 92 minus 74 is 18 squared is 324. Add them all up, divide by 3, we get another number that we don't know how to interpret, 186. So what does getting a higher variance mean? What did we say is different between these two data sets? Which also kind of falls into the idea that we would assume is true about high variance versus low variance. What's going to happen to my spread when I have higher variance? So does higher variance mean more clustered, or is higher variance going to mean more spread apart? More spread apart. So high variance, high distance or difference between my point in the middle. So high variance is the same as large or wide spread. Right, we said data set 2 was really, really spread apart. Data set 1 was really, really clustered. We get a very, very small variance for data set 1. We get a very, very large variance for, or relatively large variance for data set 2. I'm not going to make claims as to whether it's large or small. All right, questions about what variance is, like our basic definition for this? Feeling okay? Yeah.
This is going to be on the quiz on Monday.
Yes, this will be on the quiz on
And
Monday.
then,
Yeah.
Do we have to show all this work on the quiz, or just?
No. So this is me. I'm just showing you about what it's trying to do. and I'm going to show you another formula for sample variation. And then this is all stuff that we will get from the calculator. All of this is stuff that we will get from the calculator. I just want you to understand, like when I talk about standard deviation, this is like what I'm referring to. And this is like, it's not a hard process to do of like finding the differences. So if you didn't have a calculator, you could do it by hand. I actually took a statistics final where I forgot my calculator. And so I had to do all of this by hand, but our calculator will save us here and it will do all of this for us, which is nice. I just want us to kind of have that basic understanding of larger variance means more spread apart. Okay. So the other kind of variance that we can talk about is going to be the sample variance, which again is going to be fairly close to the population variance, but unlike with mean, this one has its own separate formula. Like with mean, it also has a separate way to refer to it. When we're talking about populations, we write in Greek. So we use like mu and we use sigma. When we're talking about samples, we just write in boring English letters. So this is going to be referred to as S squared. Again, that doesn't mean we're squaring anything. It's that something has already been squared. And what that something is, we're going to talk about momentarily. All right, so this is going to have a formula that's very, very reminiscent of 1.1 day one, which is to say it's going to be awful and then we're never going to use it. So this is n times the sum of all of our squared x's. N times this minus the sum of all of our x's squared divided by n times n minus 1. Sure. So again, some familiar parts. I do want to just clarify a couple of things. The first bit, the sum of the squared x's, we are squaring them first and then adding them together. The sum of the x's squared, we are adding them together and then squaring them. There's like a PEMDAS thing going on here. N is the sample size, all that. Again, our calculator is going to do this. What I want to highlight is that this is different than what we see for sigma squared. It's just a different formula. It gives us a very, very, very similar value, but it is slightly different. And the formula is very different, right? The formula is like way, way different looking. Not that different ultimately if it's going to consistently give us a similar value, but you know, looks very, very scary. So variance is kind of the place we start. Variance is like where we talk about like conceptually distance and all of that. Standard deviation though is what we actually use. So this is just, think of this as like a better version of the variance, but I'm going to put that in quotes because I don't want to hurt variance's feelings. This is just a more commonly used version. And it is very, very literally just the square root of the variance. That's it. That's the definition. So the reason why variance is written as sigma squared and s squared is because that sigma and that s are referring to standard deviation. That's why it's an s, is because it's talking about standard deviation. So it's funny, the formula for variance is s squared. And then s is the square root of s squared, which is just like definitional and cyclical and not very useful. But variance is like the thing that you can compute and conceptually understand a little bit more directly. And standard deviation is just a modification that makes the number a little bit nicer to work with and provides it some extra context to what we can do. So sigma, which standard deviation for, is that going to be population or sample? That's going to be population because it's Greek, is just the square root of what we saw for the variance. So the square root of the sum of x minus mu squared over n. Cool. And then s, likewise, is just going to be like a copy mechanic. I'm gonna copy the page. I bet there is, but I've just been doing this because I am lazy. It is just our sample, and we are taking the square root of that. Cool. Sure. So variance is like the thing that we actually can kind of calculate by hand, and then we just convert from one to the other by taking the square root. Normally you would like start, if we were doing this by hand, we would start with the variance and then reduce that down, take the square root of that to get it down to the standard deviation. What we are going to see though is that our calculator is just going to give us the standard deviation. So if we're asked for both, we're going to start with the standard deviation, and then how would I move from the standard deviation to my variance square. Cool. Yeah. You're just going to square it rather than square rooting it, because if we start with the square root, square it to get back to the bigger one. Okay, so let's take a look at this first example here. In this case, you're being asked to find the variance and standard deviation of the sample set. Sure, we could do this by hand. Why on earth would we ever do this by hand? This is also an opportunity to play with the new toy that I got, which is I can actually show you guys what I'm inputting into my calculator rather than just saying follow along. So we're going to stat. We are going to edit. What were the data values? Nine, 7, and 13, and 7. And then we are going to stat. We are going over to calc. We're going to run some one variable statistics. And where's my X bar? There's my X bar. So this is the same place where we got that 5-number summary. You can see it down there at the bottom. But important to us is going to be the S sub X and the sigma sub X. Those are the standard deviation for both the population and the sample. Now, it's a little bit weird. Notice that we get a different standard deviation, slightly different formulas, but also notice that they're like basically the same number, right? Like the difference between 2.3 and 2.1 in this context is not very huge. Yeah.
The one that's in,
Mhm.
square, that's the variance, right?
I don't see. Okay, so we don't have any, like this isn't giving us variance yet.
Okay.
So this is just giving us standard deviation. So in this case, for our example here, am I going to use S or sigma? Is this a sample or a population? It is a sample. So I'm going to use S for my standard deviation. It'll tell you in the question, or I'll make you say whether it's a sample or a population, and then you'll use the one accordingly. And so our sample standard deviation was 2.345. Let's round it to 2.35. Yes, sigma also exists, 2.14, but we're not using sigma because this is a sample rather than the population. All right, so we have the useful one. Let's get to the useless one as well. Normally, when we take the variance, when we're given the variance, we're going to square root that to get the standard deviation. In this case, we have the standard deviation. So what should we do to get to the variance? Square it, S squared. Our variance is just 2.35 squared, which is, you can check with our calculator here. Quit. 2.35 squared works itself out to be 5.52. Sure. Calculator told us. Calculator told us.
Yeah. For me, it's shown that it's
Then you either entered your data wrong or you're looking at the wrong thing. My guess is you entered your data wrong. You should get these values.
9, 7,
9, 7, 11, 10, 13, 7.
Yeah.
Then I don't know what's going wrong, but it should be a data problem.
It like crazy.
I can take a look later, but it should be a data entry problem rather than anything else. Okay. So questions with standard deviation, questions with variance.
So if it was the O,
The sigma.
the sigma.
Yeah.
You just do the same thing, but you'd
You'd use the other number instead. So if it said that this was a population data set, then we would just use the other
you still just
sigma.
square it.
You still square it.
Oh, okay.
Yeah, it's still square it, still same deal. It's just in this case we used the S rather than the sigma. Yep, good question. Very good question. That's a fair point.
What can I say?
All right, one more thing. We've already talked about this. The idea of like larger variance, larger standard deviation means more spread. Talked about this, the difference between those two. That's fine. We don't use them, so that's fine. Our calculator gives us all of this. We're going to skip over this example. One more thing to cover. Like I said, a little bit of a shorter day today, which is kind of nice. So we're going to talk about something called Chebyshev's theorem. This is our first kind of attempt to take the standard deviation and actually try and interpret what it means in the context of our data. So the basic idea that we are going to see here is that the further away from the mean we go, the less data we should see. Right? If we're like way away from the center, we wouldn't expect to be collecting all that much data normally, generally speaking, right? In some weird cases, sure, that can happen. But generally speaking, you expect to be the further away you get from the mean, the less data that you are going to see. Chebyshev's theorem is going to kind of attempt to quantify that relationship between getting further away from the mean and the amount of data that we will see accounted for as we move away from the mean. So this is going to be like what fraction of or what percentage of our data will we find within our distribution as we move further and further away from the center. This is going to say this approximates how much data we shall see within K standard deviations of the mean, which we're gonna look at an example of. Beyond this, I'm gonna give this a little bit more context than just giving the definition here. Okay, the actual formula that we're going to use to figure out what percent of our data that we are looking at is going to give us the minimum possible value that we would see. So Chebyshev's theorem is that we will have at least 1 minus 1 over k squared. And then we need this to be a percent. So what should I do to turn a decimal into a percent? Multiply by 100. So at least this percent of data, again, with this idea of being like k standard deviations away. So same k. And importantly for this, and I would so use this as like a trick question on like a quiz or a test, this would be definitely something that I would do on that, which can't be that much of a trick since I'm telling you about it now. This only works if k is greater than 1. If k is small, then the sample itself, like what kind of distribution, is going to really mess with how much data that we're going to see. So it's harder to make that prediction. Also, when k is small, if you plug in a small value of k, you're going to get a negative percentage, which doesn't make sense. So for instance, if we were looking like 0.5 standard deviations away, plug in 0.5 into this formula, you get negative 300%. Okay, that doesn't make sense as an answer. So that we have this restriction, k can only be greater than 1, but I so could ask you to use Chebyshev's with a k equal to like 0.7, and then you would need to interpret, I can't do that because the k value is too small. All right. The other thing that's really cool about this is that a lot of our understanding of how much data is going to be represented within certain standard deviations is very, very specific to the type of distribution that we are looking at. So for instance, if we are looking at a normal distribution, which we're going to focus on Monday, I can tell you right now that if we are within 1 standard deviation of the mean, then we have about 68% of the data accounted for. That's just a number that I know off the top of my head. It's very, very famous. If we're within 2 standard deviations, then it's about 95%. I think a little bit more than 95%. And if we're within 3, then it's like 99.7%. And those are just numbers that I know off the top of my head, because this is a very well-studied distribution. Chebyshev's is universal. It works for normal distributions. It works for skewed distributions. It works for uniform distributions. It is really, really versatile, but also the result that it gives is just a minimum value, right? So it could get a result that is different, that disagrees with what we see from Chebyshev's, but it won't actually be disagreeing. Chebyshev's is just giving us the minimum possible amount of data that we would expect to see. So let's take a look, for instance, at this example. We are trying to predict how much data is going to fall within 2 standard deviations of the mean using this formula. So this is going to be, we have our formula, 1 minus 1 over 2 squared is going to be 1 minus 1/4, 0.75. And so how much of our data would we expect to see? What percent? 75, not percentile, but we'd expect to see 75% of our data within that 2 standard deviations. Okay. What would we do if it was 1.3? Again, 1.3 is more than 1, so we're still happy. If it was said 0.3, we couldn't do anything, but 1.3 is fine. Exact same idea, 1 minus 1 over 1.3 squared. And when we do this, so 1 over 0.3 squared, we're doing 1 minus this. I get 40.8% of our data, at least about 41% of our data. Okay, but like, what does 1.3 standard deviations mean? Like what on earth is that number trying to communicate? We got the standard deviation is just like a value. What does it mean to be 1.3 standard deviations away? So this is the language that we are going to really be using for a lot of the actual statistics that we're going to do. I want to show you, though, what this actually means. So let's consider back to this example. What was the standard deviation that we found here? Is that 2.35? This is one standard deviation. So what could I do to figure out how far 1.3 standard deviations should be? Don't overthink it. What should we do? No, that's overthinking it. What should we do to figure out, I know what one standard deviation is. How do I turn this into 1.3 standard deviations? Multiply by 1.3. All right, so we have 2.35. 1.3 of this is going to be about 3-ish. We'll call it 3. So 1.3 standard deviations is equal to, it's like 3.05. Okay. So we're saying that we are 3.05, 1.3 standard deviations away from our mean. What is the mean that we got here when we actually do this? It should still be in your L1, L2. What's the X bar that we find? 2.35 was the standard deviation. But what was what was X bar?
9.5.
Should be 9.5. Right? This value here. So 9.5. And so what would 1.3 standard deviations below 9.5 be? Yeah, so below the mean, we would see like 6.5-ish. Maybe we'll call it, just for the sake of rounding, 6.45. And then 3.05 above would be like 12.55. Above the mean, above the 9.5. So this is 1.3 standard deviations below. And this is 1.3 standard deviations above. And Chebyshev's is saying that this should at least be 41% of our data. That we should at least find 41% of our data in this range. Okay, so let's calculate it. How much of what's our sample size here? Yeah, so, well, we don't have to add them all. It's just for sample sizes, number of data points. We have 6 data points. How many of them fall within this range, between 6.5 and 12.5? Between...
Like 3, 4.
I think 5?
Yeah.
Yeah, everything but 13 falls within this range. And so 5 of our 6 data points, or 83% of our data, falls within this range. Is this inconsistent with what Chebyshev is saying? No, Chebyshev is saying at least 41% is going to be captured within this range. And for our data, it's more than that. It's substantially more than that, which is just going to be because of the type of distribution that this represents. But at the very least, this is like a consistent result, right? We are at least at that value. This process of like figuring out the actual number that we find when we are looking like a certain number of standard deviations, that's going to be something that we do a lot at the very end of what we're doing with this course with like confidence intervals. So we will readdress this later. But I did want you to kind of see this process and again, understand like, what does 2 standard deviations mean? Well, 2 standard deviations should be 4.7 below and 4.7 above the mean. 3 standard deviations, 3 times the standard deviation below, 3 times the standard deviation above the mean, and we're making some kind of claim that we should see some amount of our data within that range. All right, questions about our 3.3 stuff? Yeah, that's it. That's all I got. Really quickly before you go. We have a quiz on Monday over 3133. We are almost done with Unit 3. Actually, we will be done on Monday. We have like one really short section that we're going to finish on Monday. We will have a review day on Tuesday, which means when is our test going to be? Wednesday. So I know it's a fast turnaround, but this Wednesday is going to be our Unit 3 test. A little bit of a shorter unit. Unit 4 should be a little bit longer. So we are going to, so we will have that on Wednesday. Quiz is 3.1 through 3.3, and then the test is adding 3.4 basically. Yeah. 3.5 does exist, but it's just a calculator section. It's just pressing buttons. So the other thing that I want to mention really quickly, just so that we're all aware, this packet that I handed out, you didn't get one for Unit 2, but this is the homework packet for Unit 3. So that will be due on Wednesday along with the Pearsons. There will also be an online test review, which will not be taken for a grade, but I will do the same thing where I will take 5% of whatever you score on that and add it to your test grade as bonus points. So there's the homework packet and now the review, and the homework packet is the grade and the review is the extra grade. Yes, you should have gotten that on day. All right. And then you guys have the 3.3 classwork should already be posted. And I'm going to give you guys, we got about 30 minutes left. You guys have the rest of this time to work on whatever you need to work on.